So here we are with worksheet 10, and this first proof, I'm using a different format now, and hopefully this is more helpful. I'm going to try and write the proofs out a little bit more like I would if I were answering the problem on a test. And it might not be completely in full detail, but it'll be definitely more than I did before, because now I'm using a stylus and it's just a lot easier to write this way. So this first proof I'm going to do pretty quickly because we went over this one as a class, and I know not everyone is always able to attend lecture, but I'm just going to run through this one. So this one says, prove that every prime number p that's in the set of primes greater than 3 is either of the form 4n plus 1 or 4n plus 3 for some n that's a natural number. So we know from the division algorithm, and this is something that you could find in the recent lectures, that every natural number could be written all n in n can be, or let's say all, let's call it all a in n can be written as 4n plus 1, 4n plus 2, or 4n plus 3. I should say as one of this set. And now I could get rid of my or. And move that over. Okay. And for example, if we take 0 as a natural number, so, and it should be noted that n is also a natural number, so 0 equals 4 times 0, 1 equals 4 times 0 plus 1, 2 equals 4 times 0 plus 2, 35 equals 4 times 8 plus 3. So they're all following this form of 4 times n plus 1, 4 times n plus 2, 4 times n plus 3, where n is any natural number. So in these first three cases, I had n equals 0, and in this last case, I had n equal to 8. And the format here is 4 times a natural number plus an integer that is less than 4. So this integer int equals 0, 1, 2, or 3. And we could do the same thing and not use 4. We could do this as, I'm going to get rid of everything and start over, and we'll use the number 3 instead, and you'll see it's going to follow the same type of form, where you could write any natural number as 3n plus 1, or 3n plus 2. And the reason you don't need to keep going, let's say we wanted to call something 3n plus 3. So an example might be like the number 27 equals 3 times 8 plus 3. And that's all correct. It is 3 times 8 plus 3, so it does follow this form of 3n plus 3, but it also equals 3 times 9. So there's no reason to say 3n plus 3 because 3n is going to cover all of those cases. Hopefully that is clear. And this type of structure is going to be really useful on this particular worksheet. So now let's take a look at this problem, and this problem is actually not so difficult. So we know that the prime set is contained in the set of natural numbers. It's a subset of the natural numbers, so every prime is a natural number. So therefore, if every natural number could be written in one of these forms, then every prime also can be written in one of these forms. And the argument, or the thing that we need to prove, is that every prime could be written as 4n plus 1 or 4n plus 3. And a way we could do that is by saying that it cannot be written as 4n or 4n plus 2. If every prime has to follow one of these four forms, and it can't be 4n and 4n plus 2, it has to be 4n plus 1 or 4n plus 3. And so we could say, for the sake of contradiction. Suppose p equals 4n for some natural number n, then so yeah, for the sake of contradiction, let's say that the prime is of the form 4n, then the prime, then this p divided by 4 equals n, and n is a natural number. So, but we have a contradiction, as 4 divides p means p is not prime. But we know that p is prime, so we run into a contradiction there. The fact that we're able to divide out of 4 gives us this contradiction. And similarly, if we try the case p equals 4n plus 2 for some natural number n, we have p equals 2 times 2n plus 1. We're able to factor out this 2. So p over 2, and you could actually stop right here. You don't have to do this division by 2, but I'm just doing it because I feel like it. P over 2 equals 2n plus 1, which is a natural number, which means p is divisible by 2. But this is impossible because p is a prime that's greater than 3. So ordinarily you may think, well, it's possible that p is equal to 2, and 2 is divisible by 2, because 2 is a prime number that's also divisible by 2. But the thing is, p cannot be 2. We can't be talking about the prime number 2 because we're limited to this set of primes greater than 3. And that is how you would complete the proof, by eliminating these two options. You've limited yourself now to the options of 4n plus 1 and 4n plus 3, both of which are odd forms. You might notice that 4n is always going to be even, and when you add an odd integer to it, it's always going to be odd, and we know that the primes greater than 3 are always odd. So it should fit your intuition that this should be the case, and I think a proof by contradiction works pretty nicely here. So now jumping into question number 2. Let p be a prime number greater than or equal to 5. Prove that p squared minus 1 equals p plus 1 times p minus 1 is divisible by 3. And this one, when I look at it, I immediately think of an intuitive argument that there's a reason we're specifying this. Like, we know that p squared minus 1 is factorable like this. It's a difference of squares. So why are we specifying this? And I think the point of this, of the problem being given to you in this way, is hopefully to cause you to have this intuition that we have these, you could think of it as like 3 numbers on a number line, p minus 1, p, and p plus 1. And that's our number line. One of them has to be divisible by 3, because every 3 numbers are divisible by 3. 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is divisible by 3, 9, 6. Every 3 numbers is divisible by 3, which means you can never have 3 numbers in a row where none of them are divisible by 3. Oops. So all we really have to say here is, and we could do a rigorous proof of this, but we know that p cannot be divisible by 3 because it's a prime greater than or equal to 5. So the only way a prime could be divisible by 3 is if that prime is 3. But in this case, we're limited to the primes that are bigger than or equal to 5. And that's a big hint right there. If we just said p is a prime, then this would actually be impossible to prove, because p could be equal to 3, and 3 squared minus 1 is 8, which is not divisible by 3. So we'd have a counterexample, and we could disprove the claim. But here we are limited to primes greater than or equal to 5, and if we just plug in some numbers like 5 squared minus 1 is 24, which is divisible by 3. If we throw in 7, 49 minus 1 is 48, which is divisible by 3. So we have some examples where it makes sense and it works. Okay. So in terms of writing out a proof of this, for this to be divisible by 3, one of p plus 1 or p minus 1 has to be divisible by 3. That's a property of primes, of prime division, that when you divide some number by a prime, one of its factors has to be divisible by that prime in order for the entire expression to be divisible by the prime. So yeah, for p squared minus 1 to be divisible by 3, either p plus 1 is divisible by 3 or p minus 1 is divisible by 3, and that's proven in the lecture slides. So we could take some, like, there's a couple things that p could be. It could take a couple different forms. We learned in problem 1 that all primes could take the form 4n plus 1 or 4n plus 3. And we could try using those. It's just very inconvenient for this particular problem to use these numbers because 4n is not divisible by 3. So instead, remember how we could also describe all the primes, or all the natural numbers actually, as 3n plus 1, or 3n plus 2. And we know that 3n is divisible by 3. It has this obvious factor of 3. So for primes greater than or equal to 5, they're not going to be able to take the form of 3n, which means that p equals 3n plus 1 or 3n plus 2. So now let's do a proof by cases. So cases. If p is equal to this form of 3n plus 1 for some natural number n, then p squared minus 1 equals 3n plus 1 squared minus 1, which would equal 9n squared plus 6n. That's it, because we have plus 1 and minus 1 cancel out, and we could factor out 3. That equals 3 times 3n squared plus 2n, which is not prime. So that's our first case. And then our second case would be when p is equal to the form of 3n plus 2. P equals 3n plus 2. So p squared minus 1 equals 3n plus 2 squared minus 1, which equals 9n squared plus 6n plus 4 minus 1. That's all correct, yeah. Which equals 9n squared plus 6n plus 3, which equals 3 times n squared. 3 times 3n squared plus 2n plus 1. And I guess the ironic thing is we said at the beginning that a prime cannot take this form of 3n. A prime greater than or equal to 5 cannot take this form 3n. A prime can, because the prime could be equal to 3, which would mean n is equal to 1. But since we're limited to these primes greater than or equal to 5, we can't divide out of 3. If we could divide out of 3, it means it's not prime. And we basically just showed that if the prime is 3n plus 1 or 3n plus 2, we'll be able to divide out of 3. In both cases, we were able to factor out of 3 once we did this expression of p squared minus 1. So yeah, so that's why it has to be divisible by 3. In either case, we're able to divide out of 3. That's the important part. And now I will make a dividing line, and we'll move on to problem 3. And I'll use green this time. Okay, so let's prove that if p is a prime greater than or equal to 5, then p squared plus 2 is composite. And this one's kind of funny. So what we're going to want to do here, first off, what does it mean for a number to be composite? It's the opposite of a prime. So it means that we could factor out a number that is not equal to 1. So an example that I gave in class yesterday is 4n plus 4 for some n in the natural numbers. So 4n plus 4 is equal to 4 times n plus 1, and n plus 1 is a natural number, so 4n plus 4 is composite, because 4 divides 4n plus 4. It's divisible by 4. We could factor out of 4. These are all saying the same thing in different ways, and all of them are indications that a number is composite. So we know that p is obviously not composite in our problem. P is prime, which is the opposite of composite. It means we can't divide out a number. It doesn't have a proper divisor. So p squared plus 2 we want to say is composite. And we could think of some examples in our head again, like if we plug in 5 for our p, then we have 25 plus 2 is 27, and we know that's composite because it's 9 times 3. And if we plug in 7, we get 51, which must be divisible by 3. Yeah, 17 times 3. And if we plug in, I don't want to do any hard ones. I guess if we plug in 11, that's 121 plus 2, which is 123, which I'm sure that's divisible by something. I don't know what. You guys tell me what that's divisible by, but it's composite somehow. Maybe does 21? No. I don't know. I don't know what goes into 123, but something does. Anyway, so we want to prove this generally, that p squared plus 2 is going to be composite, and what we could try doing is give a form for this p. So we've learned a lot of ways that we could describe p. We could describe p as just a generic odd number because we know all the primes that are greater than or equal to 5 are odd. So p could be 2n plus 1. We also know p could either be, and this 2n plus 1 will describe all primes greater than or equal to 5. We could also say that it's 4n plus 1 or 4n plus 3. And in this case, we'd have to look at both cases and prove that both cases are composite. Because just if we only looked at 4n plus 1 and proved that all the 4n plus 1 cases are composite, there's still a bunch of primes that don't follow that form, that only follow the form 4n plus 3. So we'd have to show, we want to show that this is true of all primes greater than or equal to 5. I hope that makes sense to you. If we do the 2n plus 1 case, we only have to show that, because every prime greater than or equal to 5 follows the form of 2n plus 1. But if we start opening up the door to this like 4n form, or if we want to say 3n plus 1 or 3n plus 2, if we want to do some of those forms, we're going to have to prove both cases. And in this one, Professor Carbone did it with 6n plus 1, p equals 6n plus 1, or 6n plus 5. And I'm sure this should work in every case, but sometimes you run into cases where it's actually very hard to find a way to factor out a number. So I might just do a little bit of guessing and checking on this, because this is the way that you actually will do a proof yourself on a test or on a homework. Like, you're not going to know which of these methods, like method 1, 2, 3, 4, like you're not going to know which one is going to work out the easiest. So I'm just going to start with this first method because it's the simplest of 2n plus 1. We're going to see what we can do with it. And it may not work, and if it doesn't work, we're going to have to try a different method. And the reason 6n plus 1 or 6n plus 5 is a good one is because we know that the naturals follow my stylus is, oh, there we go. 6n plus 1, 6n plus 2, 6n plus 3, 6n plus 4, and 6n plus 5. So that's what the division algorithm would indicate, are all of the natural numbers would follow one of these forms. So this first one we could factor out of 6, this one we could factor out of 2, this one we could factor out of 3, this one we could factor out of 2. And so we're left with these two examples where you can't factor anything out, which means that all of our primes are going to follow those two forms. So hopefully that idea is starting to become consistent, and you're seeing different places where this idea presents itself. different forms of natural numbers and which ones could be prime and which ones can't be prime based on the ability or inability to factor something out. So we're going to try it with p equals 2n plus 1. And we're going to see what happens. So if we take 2n plus 1 squared plus 2, we're going to get, or let's just write it out correctly, p squared plus 2. And let's also specify that n is a natural number, just to make this completely kosher. 4n squared plus 4n plus 3. That's what we get. And when I look at that, I want to prove that this is composite, which means I could factor something out. When I look at this, I don't see a convenient way of factoring this. Maybe some of you guys who are really good at algebra can figure out a way to factor something out of this, but I have no idea how I would go about this. So I would see this result and I'd give up on this method and I'd say, let's try plugging in a different thing for p. So let's go to the next one. And I'll erase this. So this is like a bit of a guess and check, as I was saying earlier. Let's try p equals 3n plus 1 or 3n plus 2. And the reason this is a little more annoying is because we're going to have to do two cases. So for this case, we're going to have p squared plus 2 equals 9n squared plus 6n plus 3. That works, because that equals 3 times 3n squared plus 2n plus 1. So that is composite. And this is, I think factoring out a 3 is enough to be able to say it's composite. You don't have to say anything else. And then we do this case, we get p squared plus 2 equals 9n squared plus, is it 12n? I think it's 12n, plus 4 plus 2 is 6, which equals 3 times 3n squared plus 4n plus 2 is composite. So that works. So we got lucky. Our second try, it worked out that we basically said that p has to follow one of these two forms, which is always true. And then when we plug in either of those forms into our formula p squared plus 2, we can prove that it results in a composite number that's divisible by 3 in both cases, which is sort of coincidental and doesn't really matter. But the fact is we're able to factor out a number, and that's what shows that it's composite, and that is enough to prove this result. And you could see in Professor Carbone's answer, she uses the forms 6n plus 1 and 6n plus 5, which also work, as you could factor out a 3 from both of those as well. Cool. So now we are up to number 4, and this one is a little bit tricky, I would say. And I'm going to show you the answer that, I'll show you a couple ways of doing it, I guess. So number 4 says, we'll go with, I guess I'll go, what color? This is a good question. All right, I'm going to try blue. Okay, let p be a prime that's greater than 5. So you notice all these problems are like primes greater than 5 or primes greater than or equal to 5. So here we want a prime bigger than 5. And we have this y that's a positive integer. And p squared plus p minus y equals 0. Prove that y is composite by proving y is divisible by 2p. So this is slightly tricky, but I guess the way I would think to do this is I would say, okay, so we could change up this formula a little bit and say y equals p squared plus p. Sorry, I have a knockoff brand stylus, so it's not always the best, but I spent like $100 on this iPad, so I didn't want to spend another $100 on a stylus. It just seemed like strange to spend the same amount on a stylus as I did on the device. Okay, so we have p squared plus p, which is also equal to p times p plus 1, which is cool. So if we just take some p and we say p is since p is a prime greater than or equal to 5, greater than 5, sorry, we know that it is of the form 2n plus 1, meaning it's odd for some natural number n. And if we plug this in to p squared plus p, we're going to get 4n squared plus 4n plus 1 plus p, which is another 2. Ooh, things are getting ugly. Okay, cool. And that is equal to 4n squared plus 6n plus 2. Is that right? Yeah. 4n squared plus 6n plus 2. So we could easily see how we could factor out a 2. We can make this into sorry, this is so bad. 2 times 2n squared plus 3n plus 1. And then this you kind of have to look for, but our goal is to factor out also another p. And p we've set equal to 2n plus 1. So now we want to look at this and say, is there a way to factor out a 2n plus 1? And I think there should be. 2 times 2n plus 1. We should have to multiply that by n plus 1. Yeah. So these like I guess it's like an unfoiling that we're doing, is not always easy to see if you're not looking for it. But this problem does ask us to look for it. We're trying to divide out by 2p. Dividing out by the 2 is really simple. And then seeing that you could also divide out another 2n plus 1, or factor out a 2n plus 1, is the thing that you have to look for. And here, if you try it, you could, I think, pretty easily see that 2n plus 1, you'd have to multiply it by another n plus 1 to get this 2n squared plus 3n plus 1 term. So this is one way of proving that y is divisible by 2p, and this is, I think, yeah, this is basically exactly what Professor Carbone did in the problem. And then there's this really clever proof that a student said in class yesterday that I really liked, and I'm not going to say his name just because this is going on YouTube public, and so I'll try not to say names of students in the class, but his proof was that we know that we have that y equals p times p plus 1. We know that this is divisible by p because we have this p term right here. So y is divisible by p, and in fact we could say that y over p equals p plus 1, which is a natural number. So therefore, p divides y. And now all we have to do is show that 2 is also a factor of y. That we could divide out a 2 from y and get a natural number. So want to prove that 2 is a factor of y. So 2 is a factor of p squared plus p, which equals p times p plus 1. And the clever observation that the student made is that p and p plus 1 is a number and then the number after it. So maybe it's like 7 and 8, or it's 11 and 12, or is 31 prime? I think 31 is prime. 31 and 32. So basically the argument that the student made is that one of p and p plus 1 has to be even. And in fact, since we know p is a prime that's greater than 5, we know that p can't be even, which means p must be odd. So p plus 1 must be even and have a factor of 2. And if you could show that y, which equals, again, p times p plus 1, both has a factor of 2 and a factor of p, that means that it's divisible by 2p. So that's the proof, and I really enjoyed that. So hopefully you guys do too. And I'll see you guys on Monday. Hopefully this was helpful. And if you have any questions, feel free to reach out to me, Arya, Professor Carbone, or your classmates. Have a great day.